to control the pool descriptor, we could just fake a pending freeze list. We can set the pending freeze stat to 20x, and then it will process all the chunks that we control. So this will allow us to free these chunks that essentially are user mode chunks to any location defined by the v-link. So yeah, that is really the gist of the attack. But notice that if they address null page mappings, this would not be possible. You might be able to find, by looking down on the pool index, so it has an array of 16 entries. Below that, it's undefined, so there might be some other pointers that you could use, so that might be able to get you past the null pointer restriction. But in the end, it usually it only boils down to checking. You really just need to check the pool index, right? So this is how that looks. Yeah, ESI points to an arbitrary location. EAX is written to that location, and EAX is a user mode chunk. I'm kind of running out of time. I want to do some demos as well, so I'll skip this part, but you can do some other tricks to, write user mode chunks even if, write user mode chunks to an arbitrary location even if the link pool trees are not used. So, if you're interested in this, I'll put the slides up. You'll find a URL on the last slide. Yeah. So you basically use coalescing to unlink the chunk that you just linked into your null page pool descriptor. That will get you a pointer back to the pool descriptor instead of the pointer to the chunk that you freed. So this is the last attack. So I talked briefly about quota charge allocations, and on x86 they store the pointer to the process associated with a quota charge allocation in the last 4 bytes. On x64 they store it in the pool header. So when you free something, you essentially decrement, a value from the limit, or what has been charged. And this essentially allows you to decrement arbitrary memory. So before we go into just looking at how that works, this is just the overflow. So the top one is the x64 64-bit process pointer is in the pool header. And the other one, you're overflowing into the process pointer that is on the end of the allocation. And the cool part about the x86 part is that if you're overflowing from a chunk that is already quota charged, you don't really need to overflow into anything. You basically, the first thing you corrupt is the pointer to the process. So you can do that's like how stable you can get it. You don't corrupt anything, you corrupt just the pointer that is associated with that particular allocation. So yeah, I think I mentioned this already. I'll just skip this. This is the structures involved. So the pointer points to an eProcess. That's like the structure for a process in Windows. And then that eProcess structure has a pointer to the quota block. That structure contains all the counters for quota use limits, whatever, and it will decrement one of those pointers. So you control, since you control the process structure pointer, you control where you want to decrement as well. So this is the summary. There's still a lot of room for exploitation in Windows 7, unfortunately. I'll talk a little bit about that in the end, but they're actually, for Windows 8, they're actually addressing a lot of these attacks, so that will be cool. Everybody will be upgrading to Windows 8 when that comes out. So case studies. So I looked at some recent vulnerabilities, wanted to, as proof of concept, show that these techniques actually work. And I'm not talking just gibberish. So we looked at two different vulnerabilities. Both were perceived as difficult to exploit. I think Microsoft still rated them as, as a 1. Not sure if they did a 2 or, but by the general public, they found it pretty hard. So the first one was a pool overflow in creative palette in Win32k. And the second one was in TCP/IP.sys. That was an integer overflow that was found by Matthew Swish, one of the organizers. That was pretty cool. So this is all public. You can find the details by searching. This one was discovered by a guy called Archon, and the function did not really validate the BI curl use field of a bitmap info header structure, and the kernel had like a static size dynamic allocation, so it would always allocate like a non-page pool of a certain size. So if you didn't set a BI curl use larger than that pre-allocated size, you would overflow. The problem with this particular bug was that it would always write 4 to the most significant byte of a D word. So I guess why people said that this was hard to exploit was that we're used to doing list entry attacks where you would normally have a pointer to a kernel address. This was not possible in this case since you had a 4 in the beginning. And another thing is that the pool type is always set to non-paged. So some thought that would be hard to exploit for some reason. In this case, what we could do is that we could use the list entry link overwrite. We could also use the liquefied overwrite. But this would actually require us to repair the list. And that would require some extra work. So if there's an easier way, we would try to find that. And there actually is. Like I said just in the previous section, this allocation is actually quota charged. So the first pointer, or the first thing that you corrupt, is the process pointer associated with that allocation. So our tactic in this case is going to be that we decrement the value of a kernel mode window object procedure pointer. And the reason why I do that is because all Windows applications map the kernel, the window objects into user mode for optimization reasons. And in doing so, we can monitor the changes made to the pointers. So it's more like it's easier to visualize in a way. That's why I did it. So we'll have a demo of that just to show how that would work. So hopefully this won't take too long. Oh, it's fast. Okay. So I'll double click on the dip test file. It will do the overflow like, 200,000 times until the pointer has been decremented into user mode. Then it will map that user mode page. It will put the shellcode there, and then it will send a message to the window object. It will use that pointer as a procedure to process the message. But since we control that pointer, we put the shellcode there. So okay. So it's running kind of fast. And there we go. So that was the first demo. Next one is going to be on the pool index. This was the quota pointer. So this was discovered by Matthew last year. And the problem here was that the function did not use safe integer functions. So you did the multiplication and the integer wrapped, and you made an allocation using that value, and you would end up with an undersized allocation. I'm going to start, so this was the IPP sort destination address function. It's responsible for sorting a list of IPv6 and IPv4 destination addresses. By the way, this is a local attack. This is not remote. You can only access this by using the IOCTL, the WSA IOCTL, with the SIO address list sort command. So you would supply an address list, and with an address count, and if you provided a large count, it would add, multiply that with the size of each structure. And since there were no overflow checks, you could end up with an undersized allocation, as I said. This function would actually operate on that buffer. It would copy the user-provided address list to the allocated chunk. So it would basically, if you had an undersized allocation, it would overflow with the size of an address structure, which is 1 C bytes. And the nice thing about this bug is that you could stop copying. If there were no way of stop copying, it would actually just keep on going for a long time, because you would have like a large number anyway if you're going to do the overflow of the number, the integer overflow. But in this case, you could stop copy records, because it would do like a validation after each copy of each record. It would check that the size is 1C, and it will also check if the protocol family is INET 6, the specifier for IPv6. And this made it possible not to trash the kernel pool completely. And also the protocol check is done after the mem copy, so you can actually get a fair amount of control here, like you can see. So you'll only corrupt like the pool header and some of the chunk data. So if you can predict the object that you corrupt, you need to make sure that the object is that you don't corrupt data that you could end up causing the system to fail in some way. So in this case, we use the pool index attack to turn the overflow into an arbitrary memory write. For that to happen, we have to specify the block size to be larger than 20 hex, because we want the chunk to end up on a free list and not on a look-aside, or we need to fill the look-aside lists. And we also need to, in order to overflow into the desired pool chunk, we need to create holes. And in order to do that, we basically fill the pool with objects, and then free each every sort of object. So just a slide on what you would fill the kernel pool with. So in Windows, you have a lot of objects. You have the executive objects, the empty objects, and then you have, like in Win32k, you have the window manager objects, you have GDI objects. You can get the kernel pointers for all these objects. So it's actually you actually have a good